So this is Unit 6, Notes B, something called stoichiometry. This is basically the mole conversions that we were doing, but we're going to add in one more conversion factor, which is going to come from the chemical equations themselves. So this example started with an unbalanced equation here, which we then balance. So let's walk through that a little bit. Because we have 1 aluminum on the left and 2 on the right, we have an aluminum problem. And then since there's 2 oxygens on the left and 3 oxygens on the right, we also have an oxygen problem. This entire thing is unbalanced. I usually start with the oxygens because they're the most complicated. If I have 3 on one side and 2 on the other side, the lowest common denominator there would be a 6. So we're trying to get 6 total oxygens on both sides. So if I have sets of 3 on the left, then I would need 2 pairs, or 2 sets of 3 I should say, in order to get 6 total oxygens. That then creates 4 aluminums total, which is where the 4 comes in for balancing the aluminum on the left. For the oxygens on the left, they come in pairs, so I would need 3 of them to get 6 oxygens on the left. That balances it with 4 aluminums and 6 oxygens on both sides. So now that we have a balanced equation, what does that tell us? We're going to take this to the next step. So this is all about proportions. 4 aluminum atoms will react with 3 oxygen molecules, and then that combined makes only 2 product particles, the aluminum oxide particles. So a proportion can be set up as a conversion factor. 4 moles of aluminum is proportional to 3 moles of oxygen, or I could also bring in 2 moles of the aluminum oxide. And any of that I can set up over each other, and that would be a conversion factor that we're going to use now in stoichiometry. So now whenever we balance an equation, we have determined the amounts that the particles react with each other. And that can be used as a ratio in order to get a conversion factor. It's really important to note that it's only this mole ratio that's going to tie into the coefficients of the balanced equation. We are going to use some of the equivalencies from Unit 5, but all of those were equal to 1 mole then, and they're equal to 1 mole now. That never changes. So 22.4 liters is still only equal to 1 mole. Avogadro's number of particles, still equal to 1 mole. The molar mass, the number of grams in a substance, still equal to 1 mole. It's only when I compare the amount of one thing to the amount of another thing, when I have moles in both the top and bottom, that you will have a number other than 1. So we're going to use this equation for the next couple examples. We have iron 3 oxide, the 3 meaning a plus 3 on the iron, hence the 3 outside of the oxygen, and then a minus 2 of the oxygen. So the formula for iron 3 oxide is Fe2O3, that's also known as rust. That's going to react with carbon monoxide, which is just CO. It's going to form iron, regular Fe, and carbon dioxide, CO2. So that would be unbalanced, just given the formulas. So you see the coefficients to balance the equation, the 1 for the iron oxide, 3 for the carbon monoxide, 2 for the iron, 3 for the carbon dioxide. You need a balanced equation in order to do any of these calculations, because that balanced equation is going to help us with our mole ratio. So now our first question. How much carbon monoxide is required to react with 25 particles of the iron 3 oxide, or Fe2O3? So that 25 particles of the Fe2O3 is my given to start the math, which you can always write over 1 because we want to make sure that we treat that as the numerator. Now we're just comparing generic amounts, how much. So I don't actually care what type of particle. All I care is about a ratio, a mole ratio. So see how I'm just using moles as my given? That basically says for every 25 particles or amounts of the Fe2O3, how much other stuff is used. So now that I have my given set up here, 25 moles of Fe2, I'm going to use a skill we started with dimensional analysis. Whatever units I have on the top go to the bottom of the next conversion factor. So if I have moles of Fe2O3 on the top, I shall bring moles of Fe2O3 to the bottom. What I want to convert to this time is not grams or liters, but actually how much of something else. So again, I'm using moles, but now I'm going to specify what my other thing is that I'm trying to find. The question says we're trying to find how much carbon monoxide. So I'm going to use my mole ratio to convert from moles of the iron 3 oxide to the moles of the carbon monoxide. Then the question becomes, where do I get the mole ratio numbers from? And the answer is from the balanced equation. To find out how much of the Fe2O3, I have to look at the balanced equation. The coefficient there is 1, so that is the number I will use in front of the coefficient for the moles of Fe2O3. In order to find out how much carbon monoxide to use in the conversion factor, I'm going to look at the carbon monoxide in the balanced equation. The coefficient is 3, so that's the number that I'm going to use in front of the moles of CO in the conversion factor. So we can see that our units cancel. The moles of Fe2O3 cancels with moles of Fe2O3, and I have moles of carbon monoxide as the unit for my final answer. Now simply to do the math. So in the calculator I would type in 25 times 3 and then divide that by 1 only on the bottom. So basically 25 times 3 is 75. For significant figures, I started with 2 significant figures, so I'm going to end with 2 significant figures. So the final answer is 75 moles of carbon monoxide. We really do want to start including the substance in the units, because unlike last time when you were dealing with the same substance in the beginning and end, we are actually converting from one substance to the other. So we want to know what substance we are ending with as our product. Let's look at another question. How much iron can be produced by the reaction of 2.5 times 10 to the 5th particles of Fe2O3? So it gave me Fe2O3, so I'm going to start off with Fe2O3, this 2.5 times 10 to the 5th of the Fe2O3. Again, because I'm just comparing relative amounts, I can just simply use moles. I don't actually care what kind of particle it is. So my given is 2.5 times 10 to the 5th moles of Fe2O3. And you can put that over 1. So that's going to start off our math. We started with moles of Fe2O3, so automatically on the bottom of the next conversion factor, we are going to put moles of Fe2O3. Same exact way that you used to do dimensional analysis and mole conversions. Whatever goes on top, we then bring to the bottom in order for it to cancel out. So then the question is, where do we go from here? And again, we're not doing grams or liters anymore. We're trying to convert to a different substance. So what are we trying to find this time? That would be the amount of iron. Because it says how much iron, I'm going to use iron in the numerator. So my conversion factor is the moles of iron over the moles of Fe2O3. Then the question becomes, where do I get the numbers for that conversion factor? And again, the answer is the balanced equation. So in order to figure out what to put in front of the moles of Fe2O3, I'm going to look at the Fe2O3 in the equation. You can see the coefficient is 1, so we're using 1 in the conversion factor. If I wanted to find out how much of the iron to use, I have to find just pure iron in the equation. The coefficient is 2, so I'm going to use 2 in my conversion factor. So now that we have our math set up, we can check and make sure our units cancel. The moles of Fe2O3 cancel, leaving me with moles of Fe for my units. And now I just need to type into the calculator 2.5 times 10 to the 5th. Remember to use the E key for your exponent, 2.5 E5, and then times that by 2. So basically we get 5.0 times 10 to the 5th. Again, starting with 2 sig figs, so ending with 2 sig figs. So for correct sig figs, you do need that 0.0. So that gives you a final answer of 5.0 times 10 to the 5th moles of Fe. All right, now we're going to take it up a notch. First, let me highlight the part of this example that we were working with in the last 2 examples. We were given an amount of one substance, which we then put on the bottom of the next conversion factor and used the mole ratio in order to convert to another substance. The only difference with this type of question is that we're not starting with moles. Instead, we're going to start with grams and use the molar mass in order to get to moles. And not only that, we're not going to leave our answer in moles. We're going to use the molar mass to get back to grams, but of a different substance. So you can see the molar masses are different because they are for different substances. So the basic format here is that you use the unit 5 conversion factors in order to go from gram to mole using the molar mass. You use the mole ratio in the middle. And then at the end, you're going to go from mole to gram. Again, something we've done a lot using the molar mass. Notice outside the mole ratio, it's still 1 mole. It's only in the mole ratio where you're going to take your numbers from the equation. So they will be something other than 1, or can be something other than 1. So let's go through this from the beginning. The only number they give us in the question is that I have 146 grams of the iron oxide. So that is my given, which of course you can put over 1 because we want that in the numerator. And then whatever unit I have, grams of Fe2O3, will have to be the unit in the bottom. That's basic dimensional analysis. You cannot go immediately to moles if it gives you grams. So how do we go from gram to mole? We use 1 mole of the substance and use the molar mass of Fe2O3. So in order to calculate the molar mass, just as a reminder, you would take the molar mass from the periodic table for 2 irons and 3 oxygens and add that all up together, and you would get 159.6. So then if we set that equal to 1 mole, because 1 mole is always equal to the molar mass, we can then be in the units moles of Fe2O3. So now that we have moles of Fe2O3, we will automatically put moles of Fe2O3 on the bottom. Basic dimensional analysis, top to bottom. Now what do I want to convert to? Well, here's my opportunity now that I'm in moles to convert to another substance. So now I can go to moles of carbon monoxide. How did I know I wanted to go to carbon monoxide instead of any of the other stuff? It's in the question. How much carbon monoxide? There is a problem that it says mass. That's what we're going to take care of next. But first, let's finish this. How do we know the numbers to put in the mole ratio? That always comes from the balanced equation. So in order to find the number to use for Fe2O3, I go to the balanced equation where the coefficient was 1 and use 1 with the Fe2O3. In order to find the coefficient for the carbon monoxide, I find the carbon monoxide in the balanced equation. The coefficient is 3, so I use 3 in the mole ratio. So now that I have carbon monoxide, I'm going to take care of the part where the question asks for mass instead of moles. So automatically, since I have moles of carbon monoxide on the top, I will bring moles of carbon monoxide to the bottom. And then in order to go gram to mole, we will use the molar mass. So again, we know that the molar mass is equal to 1 mole. So we would take from the periodic table the mass of a carbon, which is 12, and the mass of an oxygen, which is 16, which add together to give you 28. So a question that I get a lot at this point is, do you triple that because you have 3 of them? And the answer is no, you'd be doing it twice. We already took care of the fact that there are 3 of them when we set up our mole ratio. So you wouldn't want to triple it again at this point. 1 mole is always equal to the molar mass. So we always use 1 mole outside of the mole ratio. So now that we have our conversion factors all set up, let's double check our units. Grams of Fe2O3 cancels with grams of Fe2O3. Moles of Fe2O3 cancels with moles of Fe2O3. Moles of CO cancels with moles of CO. And so the only thing left is the grams of CO, which is going to be my unit. Don't forget to include the CO now. So now we're just going to type in the math. We're going to do 146 divided by 159.6, since it's in the bottom. I would hit enter there, and then take that number and multiply it by 3, and then take that number and multiply it by 28, and you should get 76.8, starting with 3 sig figs, ending with 3 sig figs. So my final answer is 76.8 grams of carbon monoxide. So last example here, let's look at our basic setup. So it's giving me grams of carbon dioxide and asking for mass or grams of iron 3 oxide. So again, we're starting with the given of grams and converting to moles, gram to mole. Then we're going to convert from mole to mole using the mole ratio. And then we're going to take care of answering for the mass by going from gram to mole. Oh, sorry, backwards. By going from mole to gram. So this is kind of a repetitive thing. We basically need to get into moles and then get out of moles. But you always have to get to moles so you can convert from one substance to the other substance. So starting at the beginning, the only number it gave us was the 8.65 grams of carbon dioxide. Notice this one does say dioxide, so we're dealing with the product this time. So we're starting off with that 8.65 grams of CO, which of course you can put over 1 if you want. So then whatever we start with, we will automatically put those units in the bottom, grams of carbon dioxide. We don't want grams, we want moles. So how do we go from gram to mole? Well, we know that the molar mass is equal to 1 mole. So we're going to use 1 mole of the carbon dioxide and set that equal to the molar mass of carbon dioxide. So carbon being 12, oxygen 16 twice adds up to 44. So now I am in moles of carbon dioxide. So if that's what's on the top, I will automatically bring moles of carbon dioxide to the bottom. Now that I'm finally in moles, this is my chance to convert to a different substance, my mole ratio. The question becomes, where do I get the numbers to use for the conversion factor? And when you're in the mole ratio, and only in the mole ratio, the answer is from the balanced equation. So in order to find how much carbon dioxide, I'm going to look at the product, 3 CO2s, so the coefficient is 3. I use that in my mole ratio conversion factor. Now I want to find the coefficient for the Fe2O3 to solve how much to put in the top of the conversion factor. So if I look at the Fe2O3 in the equation, it has a coefficient of 1. So that's what I'll use in my conversion factor. So now that I have Fe2O3, the last thing I want to take care of is getting mass instead of moles. So it comes back to, again, that the molar mass is equal to 1 mole. So I'm using mole on the bottom because I had mole on the top here. So I'm going to use mole on the bottom, and that's going to be 1 mole always, equal to the molar mass. So the molar mass of Fe2O3 is 159.6 if you add up the molar mass of 2 irons and 3 oxygens. So now that we have our conversion factors all set up, let's double check our units. Grams of CO2 cancels with grams of CO2. Moles of CO2 cancels with moles of CO2. Moles of Fe2O3 cancels with moles of Fe2O3, leaving grams of the iron oxide as my final answer. Final answer is units, I should say. To get the answer, we still have to go in and do the math. So I would take 8.65 and divide it by 44. I would hit enter there and then also divide by 3, hit enter again, and then multiply by 159.6. You could also multiply 8.65 and 159. Separately multiply 44 and 3 and then divide those answers. But be very careful with the parentheses or order of operations in that one, because you do want to make sure you're dividing by both the 44 and the 3. And sometimes when you hit multiply, because these would multiply by each other if you kept them on the bottom, the calculator gets confused and tries to multiply the entire answer by 3 and not just the 44. So try it, see what you need to do in your calculator to get the answer. Should be 10.5. And there are 3 sig figs in the given, so with 3 sig figs, my final answer is 10.5 grams of Fe2O3.